So welcome everybody. Today I thought we would talk a little bit about what's been up in the sky, what's happening, review a little bit, find out if anybody saw the lunar eclipse last month. It was a miracle here in Ithaca. And also take a look at how it would be viewed from the moon and actually look at what was seen by a lunar lander. And then I thought we'd talk about dark matter. So, first of all, astronomical highlights. The moon will be full on the 13th of April and then new on April 27th. Tonight, the moon will set at about 5:35 p.m. and rise at 5:15 in the morning. And it's in the waning crescent phase and it's almost new. There will be a new moon on March 29th, and we'll talk in a minute. It turns out that right around sunrise, there will be a partial eclipse visible from Ithaca. However, I will warn you, it's not that easy to see. And of course, there's the issue of clear skies, especially in the morning. Okay, other things, Mercury right now is in the glare of the sun, but it will actually be moving away from the sun. And so it will be visible in the eastern sky just before sunrise later in April. Venus rises an hour before sunrise. Mars sets in the early evening. Jupiter is visible in the west for the first hours of the evening. And Saturn will be visible early in the morning just before sunrise. For the last few months, we've had a good view of a lot of the planets, but right now they're switching over from being visible in the evening to being visible in the morning or not being visible at all. But there is an interesting thing. Should you happen to be up before sunrise on April 17th, 3 of the planets will be visible in roughly the same part of the sky. This is a view of what it will look like. This is actually from the southern hemisphere, but it will look pretty much the same from here. Venus, Saturn, and Mercury are visible to the naked eye. Neptune is not. It happens to be in the same location. But that will be where we had a planetary parade last month where there was visible but spread out over the whole sky. Here are 3 planets that are roughly in the same part of the sky and are visible to the naked eye right before sunrise on April 17th. So for those of you who are early risers, you can look for that. The other thing, as I mentioned before, is the partial solar eclipse on March 29th. You see the maximum eclipse is on Saturday, March 29th. That's 6:55 a.m. But unfortunately, it's only a little bit of an eclipse. And so, in fact, all one would be able to see, even though it's a little bit of an eclipse, you should wear eclipse glasses. But if you look at the sun at the maximum, you'd see a cutout of part of the sun being blocked by the moon. It's tough to observe when it's so close to the horizon, but nonetheless, if anybody's up early and it's clear, you can take a look. Just now back to lunar eclipses. So that's a solar eclipse where the moon blocks out the sun. Last month, we had a lunar eclipse where the moon passes through the Earth's shadow, as we talked about the last time. And I wonder if anybody saw it. I did. It was miraculously clear weather in Ithaca.
I did too.
You did too? Great.
Yes, me too.
It was a miracle. It was also at 3 o'clock, 2:30, 3 o'clock in the morning, but. And so here's just a nice picture taken, a montage of a couple of pictures of the moon. The moon, when it passes fully into the Earth's shadow, doesn't become completely dark because the Earth has this thing called an atmosphere. And the atmosphere bends some of the sunlight and has it reflect off the moon. And it bends different colors of sunlight, different amounts. And the blue light gets scattered away, and we preferentially see the red light. And so when the moon moves through the Earth's shadow, we get what we call the blood moon. The moon where more of the blue light has been scattered away and the red light has been scattered back towards the Earth. And that's why we see it. Now, the other thing I thought we'd talk about is just the idea of what would happen if we wanted to watch a lunar eclipse as seen from the moon. So here's a little animation that shows that. So here's the Earth. Now, the Earth, as seen from the moon, is bigger than the sun. Remember, we said that one of the strange cosmic coincidences is that as viewed from the Earth, the moon and the sun are the same size in the sky, even though the sun is much, much bigger than the moon. That's not true as viewed from the moon. The Earth is much bigger than the sun is. We can watch that again while I talk. The Earth you can see here in this animation is bigger than the sun. And so the sun goes completely behind the Earth and you don't see any of the prominences around the edge. It's completely covered. Now, it just happens that around that last month, there was a lander on the moon called the Blue Ghost 1 moon lander, and it happened to watch the lunar eclipse. So let me play that again. This is a view. It had a fixed camera looking out, and it just happened that part of the time that it was sitting there looking out, there was an eclipse for it. And so that's what that lunar eclipse looked like from that lunar lander. Kind of neat that we can actually observe astronomical events from other bodies in the solar system. Okay, so anybody have any questions about any of that? Okay, then I'll move on to the stuff that I don't know anything about. We'll talk about dark matter in the universe. Now, the fact is, I'm not the only one who doesn't know anything about this, so I'm in good company. So I thought we'd talk about dark matter. We talk about why dark matter is important and why we think it exists. We're going to start with the easy question first, which is why is dark matter important? So we have to go back to our discussion, which we had last fall about the Big Bang and what is the Big Bang. And as I said then, something like 98, 99%, there are always a few odd people or people who don't want to be in the mainstream who don't believe in the Big Bang model. But most astronomers believe that about 19.7 billion years ago, the universe was much smaller, much hotter, and much denser than it is today. And there was an event that took place at that time everywhere in the universe that we call the Big Bang. And since then, the universe has been expanding, but there was a tremendous release of energy that sent everything in the universe expanding. And so the question naturally comes up, what happens? How is that expansion going to happen historically over time in the past and the future? Is the expansion speeding up? Is it slowing down? Is it just expanding at the same rate? What's happening? And so we have to think about that in terms of galaxies, that in earlier times, galaxies were closer together, and at later times, they were further apart. And our understanding up until the late 1990s was that there's this expansion, but we also know that gravity is an attractive force. And the idea was that the attractive force of the gravity of all of the mass, the stars, the planets, the galaxies, the rocks, the black holes, everything, should act to slow down the expansion because gravity is attractive. But it turns out it's not that simple. So let's think about the possibilities for what could be happening. So here are little cartoons which show this is time on the vertical axis, and these are supposed to represent the 3 dimensions of space in the universe. Remember, when we talk about cosmology and the universe, we have to talk about space-time, the space at a time. And time evolves, it goes from the past to the future. And we could have a case where the universe expanded, reached some maximum size, and fell back in on itself. We call that the recollapsing universe. We could have what we call the critical universe, which is where the universe doesn't collapse. It always is expanding, but it expands ever more slowly with time. That's the critical universe. We can also have something called the coasting universe, which is that it expands forever, but at some point it just is expanding with little or no slowdown. Or we have what we call the accelerating universe. The universe is expanding, and yeah, at the beginning it tried to slow down. Gravity tried to hold on to it, but gravity wasn't strong enough. Instead, there was another force in the universe that caused the expansion of the universe to accelerate. And we call that the accelerating universe. And this is, in fact, the one that we think is the true universe, the real universe, although we don't understand that. We'll come back and talk about that at the very end. But this is the universe that we think is happening, but there is dark matter, in fact, in the universe. So we call this accelerating universe the cold dark matter plus lambda. Lambda is an expression or a symbol that Einstein introduced into his theory of the universe and relativity and gravitation to keep the universe from collapsing under its own gravity. He didn't know what it was. In fact, he called it the cosmological constant. And he put it in there before he knew that the universe was expanding. So later on, he said it was a big mistake that he made, and we should all make mistakes of that nature and only those mistakes. He was pretty right about everything else. But then we can take a census of what's in the universe. And so what we're really asking is how much energy density is there in the universe? And we are going to benchmark that to the critical universe. So if there's a lot of density in matter, we could get a recollapsing universe. If there's not a lot of density in matter, but there's a lot of density in something else, we could end up with the accelerating universe. So the total census of the universe consists, so that's what we call lambda total, consists of matter, and matter is stuff that partakes in the gravitational force, pulls on each other. We also know that there's a component of the universe that's made up of light, radiation. Radiation carries density, energy. And what we're talking about is the total amount of energy in the universe. And we also have a contribution that we're going to call the contribution due to dark energy, or this thing that we call lambda. What we're going to focus on today is the contribution to the total energy of matter and motion in the universe, of everything that relates to the gravitational force. We're going to call that omega matter, and it consists of omega dark matter and omega baryons. Baryons is just a fancy word derived from the Greek, maybe heavy ones, which means normal stuff. Okay, so what we know today is that if we take a census of the universe, only about 5%, 4.9%, is contributed by the stuff that we understand. Stars, planets, atoms, molecules, galaxies, everything that we understand, the baryonic matter, 5%. The other 95% of the universe, we don't know what it is. We think that about 26.8% of it is dark matter, and 68.3% is this dark energy stuff, which is what makes the universe accelerate. And I'm not even going to go there at all today. We're only going to focus on this dark matter stuff. But we do understand that there are clues to what dark matter and dark energy are in the early universe and how the early universe formed, and also in our understanding of the fundamental particles, the elementary particles, the stuff that makes up atoms and electrons and other fundamental particles. And we'll come back to that at the end. Okay, so let's keep in mind, we want to take a census then. If we want to figure out which one of these models of cosmology is the true one, we have to go out and observe the universe. So what do we observe? So here's an old picture from the Hubble Space Telescope, but it's a very famous one, one of the original Hubble Deep Fields. And this cutout here is due to the way the camera was designed. It had a cutout in it to hold, it wasn't completely filled. And what we look at when we see this picture is we are looking, when we look at the optical wavelengths, we're looking at starlight in distant galaxies. We don't understand which one of these galaxies is nearby, which one is further away, but what makes the light that you see in this image is starlight. The universe is expanding, but the matter, the mass that is contained in all of the stars and all of the galaxies here, we want to know how much mass there is. And can the gravity of that matter halt the expansion? Remember, I've already given you the answer. The answer is there's not enough matter, and there's this dark energy thing. But how did we actually figure out how much dark matter there was and why we needed to have dark matter? And that's what we're going to talk about. So how much matter does the universe contain? We don't observe matter, we observe light. And then we have to figure out, if we observe that much light, how much matter is there? We have to estimate how much mass there is to give off the light that we see. And so that's our problem today. So let's go back and just remember a few things that we've talked a little bit about before and that you're also familiar with. We have satellites and we put them into orbit. And we have different satellites have different orbits. Some are elliptical, some are circular, some are close to the Earth, some are further than the Earth. Sometimes we give satellites enough push that they escape the Earth's gravitational field and go off and go to the moon, or they go to Mars, or they go to Jupiter or somewhere else. And what determines what happens is how much energy of motion, what we call kinetic energy, we give to a satellite. If we want the satellite to get into this orbit versus this orbit down here, we have to give the one that goes further away from the Earth more energy of motion. For a satellite to stay in the circular orbit, for example, it must have kinetic energy that balances the gravitational pull of the Earth, trying to attract it back to the surface of the Earth. We can relate those to forces. There's a force that's associated with the satellite's motion, and probably you've heard at some point that that's mass times acceleration as a force. And that energy of motion has to balance the gravitational force that the Earth is exerting, trying to pull the satellite back to the ground. If there isn't a balance, the satellite will either fall back to Earth if it doesn't have enough kinetic energy, and if it has too much, it will actually escape and go off and leave the Earth's gravitational field. So again, let's think back for the planets. We know the planets are in orbit around the sun. The planet's orbital velocity has to be exactly the right amount to balance the force. If there isn't a balance of the energy of motion and the energy of the gravitational force of the sun pulling on the planet, then the planets would either fly off and become independent of the sun, or they'd fall into the sun. And it was these laws of mechanics that Newton came up with that gives rise to Kepler's laws of planetary motion, which basically say that the planets must travel at the right speed to stay in orbit, according to their distance from the sun and the masses of all. Now remember, in the solar system, the sun is the big mass, and all the other planets have much, much smaller masses. And so the mass of the sun dominates. In other systems, like in galaxies, there are lots of different stars that have similar masses. And so we have to take into account all of the masses. But the bottom line is that for a planet to stay in orbit around the sun, the forces must balance. And the forces are the gravitational force pulling the planet into the sun versus the force associated with the planet's motion, which has to do with its mass times its acceleration. This same kind of idea we're going to use to measure the mass of other objects. And again, if the force exceeds the gravitational force, the satellite will escape. So the velocity has to be fixed to achieve this balance. Okay. So again, we go back to our idea that there are galaxies which contain billions of stars, and there are billions and billions of galaxies. So our problem has been that we can calculate the mass of a galaxy by looking at it, figuring out roughly how many stars it must have from how much light it gives off. We know that stars of a given brightness, we talked a little bit about this before, stars of a given brightness have a given mass. The stars' luminosity and mass are not random. They sort of depend on one another. And so we can add up all the light given off by all the stars in a galaxy. And the problem is that there isn't enough luminosity to account for that mass. And therefore, we invoke the term dark matter for the mass that we cannot see, but which exerts the gravity needed to keep the stars from escaping the galaxy, or we'll see later, galaxies also have a tendency to come in clusters of galaxies, and we don't want the galaxies to escape from them either. So let's take a look at a little more look. So first of all, as an example of the fact that dark matter could be stuff that we just can't see, not because it's weird or unusual, but because we either don't know how to detect it because it gives off weird kind of light, or because it's too faint for current telescopes to detect. But if we build a better telescope, we can see it. And an example of this is the planet Neptune. So in 1781, William Herschel discovered the planet Uranus. And again, people understood Kepler's laws up until that time, and they could even make predictions because they knew Kepler's laws of where you should be able to observe Uranus over the years. Uranus doesn't move very fast because it has a very long orbital period. But by around 1830, astronomers had noticed that Uranus doesn't seem to be quite in the right place. It's wandering. And so John Couch Adams, who was a student at the University of Cambridge, was given the task for his research to investigate why it is that Uranus might not be in the right place, under the hypothesis that if there was another planet out there that hadn't been discovered, that was further than Uranus, perhaps it was exerting a little bit of gravitational force on Neptune, on Uranus, and therefore causing it to deviate from its path predicted, knowing only the other planets and the sun. So Adams in 1845 predicted the position of Neptune, and it turns out that the French mathematician Leverrier thought of the same idea and independently also predicted a position for Neptune just a year later. And astronomers ran off, and the weather was bad in England, and so the Neptune was discovered in Berlin. Now, theoretically, therefore, or technically, therefore, Neptune was dark matter before its discovery. Why? Because it was dark. It wasn't known. People didn't know that it existed. They didn't know where to look. They had never observed it. but it exerted a gravitational force on an object that could be seen. And therefore, the fact that it perturbed the orbit of Uranus, because Neptune has mass, allowed Adams and Leverrier to figure out where astronomers should look for Neptune. So it's possible for dark matter to become visible matter if you can infer that it's there and therefore figure out how to see it. Okay, so a little history of dark matter. Again, the idea starts with the fact that even in early days of telescopes, astronomers were able to realize that if you observe the motion, some stars move. And so in 1884, Lord Kelvin estimated, based on the observed motions of stars, that there might be many dark bodies that were out there that exerted the gravitational force, that were some different kind of stars, and therefore were not visible. In 1922, Kapteyn looked at the motions of stars and noted that it is incidentally suggested that when the theory is perfected, it may be possible to determine the amount of dark matter from its gravitational effect on visible objects. And that is going to turn out to be one of the fundamental ways that we infer that there's dark matter. In 1932, Jan Oort was measuring the motions of stars perpendicular to the Milky Way galaxy. Remember, this is not the Milky Way, this is another galaxy, but the Milky Way is a disk galaxy. And what Oort was doing was observing the motions of stars perpendicular to this disk in our own galaxy. And he said, they're moving too fast. Why are they moving fast? What is causing them to move fast? And the answer is it must be because there's more matter there than you can see. There's more mass in stuff than you can see. Now, the real term dark matter and the real understanding of dark matter came about later by the work of Fritz Zwicky, who was a crazy guy. But I will tell you that my first cat was named Zwicky. And he was observing galaxies and clusters of galaxies. So this is a modern day picture of the Coma cluster of galaxies. Nearly all of these objects are not stars. They're located about 100 million light years away. They are galaxies, and they are orbiting around a common center of mass, which is located somewhere around here. They are orbiting around, and so here's the cartoon of what I mean by orbiting around. There's a center of mass, and some of them are orbiting this way, and some of them are orbiting this way, and some of them are orbiting that way. But they're orbiting around the center of mass, and if we watch them over billions of years, the universe expands, but these objects, just the same way that the planets stay in orbit around the sun, these galaxies stay in orbit around the center of mass of this cluster. And therefore, we know that their velocities must be set so that the gravitational potential of all of the mass in that cluster is balancing the energy of motion of all of the galaxies in their orbits. Because if there weren't that balance, the cluster would either collapse or it would expand. So in 1933, Fritz Zwicky measured the velocities of stars in individual galaxies in the Coma cluster to get the galaxy's mass. And he did this for very few objects, I should say. He said we can measure the velocities of galaxies in their orbit to get the mass of the cluster as a whole. So we have the mass of the galaxy, and we can add up the galaxies to get the mass of the cluster. We can make some assumptions about how these masses scale with the total number of galaxies in the cluster, because he could only observe some of them. But basically, he asked the question, if there's a balance between the gravitational potential energy and the kinetic energy of motion, and I can measure the velocities of the galaxies, then I come up with the mass of the cluster. And I can also, understanding what I know about galaxies, figure out how much mass there is in the galaxies, in the light from the galaxies. And again, the bottom line is, he said, the galaxies are moving too fast. to be held in their orbits simply by the light that I can see. And so he really invented the term dark matter. And so his idea, what he said was, if this overdensity is confirmed, we would arrive at the astonishing conclusion that dark matter is present in coma with a much greater density than luminous matter. And so he said, this is an unsolved problem. Well, we've been talking about this for the intervening period since 1933, for the intervening 90 years, and we know something more, but a lot of what the evidence for this goes back to this theorizing by Zwicky based on very few observations, in fact. Okay, only 5% of the total energy density is luminous. Dark matter makes up 85% of the matter of the universe, so it seems like it would be a good thing for us to figure out what it is. And so we're going to talk about clusters of galaxies and two phenomena. We can measure the motions of the stars, of the galaxies, and we can measure dark matter. And we're also going to use a phenomenon known as gravitational lensing, where galaxies in the foreground act as lenses to make images of galaxies in the background. So we'll talk about that. So what's the evidence for dark matter? The first evidence is what I just talked about. What's Zwicky found? The orbital speeds of galaxies and clusters are higher than the amount of mass we can understand in stars and galaxies, in dark matter in the galaxies themselves. In other words, there's dark matter, not just in galaxies, but in between the galaxies. And we also haven't really talked about it, but we also have to take account not just of stars and gas, but also hot gas that fills the whole cluster in what we call the intracluster medium that wasn't known about when Zwicky made his hypothesis of dark matter, that's only visible using X-ray telescopes. So again, here we have a little simulation of what we're trying to think of. We start out, here's a bunch of galaxies inside a cluster that is mainly composed of dark matter. And now if we watch the galaxies over time, you see that they are orbiting around this dark matter. The dark matter is pictured here. Obviously, we can't see it. But the fact that the galaxies stay in orbit mainly and move around, some of them faster than others, that tells us how much mass there is in the dark matter, which is required to keep the galaxies, the gas, and the dark matter from escaping. Okay, so again, we can calculate what we call the virial mass, and I've just written it down here. It's the equation we can write down if we want to balance the gravitational energy and the energy of motion. And to make it, all we have to do is observe the cluster's extent, observe the velocities of all these galaxies, and then make the assumption that the gravitational energy must balance the energy of motion. And so we really just have to measure the radius of the cluster and the mean orbital velocity, the average velocity of the galaxies in the cluster. And what we find out every time we do it, every time, is that there is much more mass that is required to keep the cluster from collapsing than we can account for in the sum of all the individual galaxies and the hot gas. Okay, so I'm just going to say that an example of the very nearest cluster of galaxies, there is 10 to the 15. So write down 10 and then write down 15 zeros. And times the mass of the sun, that's how massive the cluster is. It's just a big number. I don't have a feeling for it either. It's just really, really big. But in fact, if we look at how much mass is in the luminous mass, 82% of the mass of the cluster is not visible to us. Okay, so problem. Okay, next thing we can do, again, we want another piece of evidence. Dark matter is important. We need to know if it's really true. So we need some other evidence. that allows us to convince ourselves that dark matter exists. So now, instead of looking at clusters of galaxies, let's look at individual galaxies. Individual galaxies, if you look even in the Hubble Deep Field, they have an edge. They end. What that means from the pictures is that their luminous matter ends. But when we measure the speeds of the stars in orbit around the galaxy, they continue to have very high speeds. The mass doesn't end. The luminous mass ends. And we say, therefore, that galaxies have dark halos. So we have to think of what's happening in a disk galaxy like the Milky Way. Again, the Milky Way is a flattened disk. And the sun is in orbit at about 30,000 light years from the center of the Milky Way. It has a little bit of up and down motion, but most of its motion is in the plane of the disk. And we assume that the Milky Way has lasted for a long time, and that the reason that the sun stays in its orbit is that our velocity, which is about 220 kilometers a second, is just right to keep the sun in its orbit so that it doesn't fall in or it doesn't escape from the Milky Way. So just as we can observe the motions of the different planets in the solar system, we can figure out how massive the sun is. We can also do the same thing for galaxies. So let's think, we can ask ourselves, how does the velocity change as you move from a planet that's close in to the planets that are far out? In the solar system, that basically tells us Kepler's third law, that if you look at the planets, so here's Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and here's even Pluto. This is an old diagram, so it has Pluto as a planet. If we look at their orbital velocity, Mercury is moving at about 50 kilometers a second in its orbit. The Earth is moving at only 30 kilometers a second. And we get out to Jupiter, it's only moving at about 12 kilometers a second. And we see this very characteristic fall off. The further out you go, the planets are moving slower. And that has to do with the fact that as you get further and further away, the gravitational force becomes weaker, but you also have to travel around. The energy of motion has to balance the gravitational potential energy that the planet feels at that distance. So in the solar system, all the mass is contained at the center. And that is why this works. But the problem is that spiral galaxies don't behave this way. We understand all of the mass in the solar system. The sun is the big mass, and the planets do have mass, but much less. On the other hand, when we look at galaxies, we see something very different. So we could also ask ourselves, what would we expect? So in the solar system, we see what we have Keplerian decline. We just also mention that if you have one of these little rotating wheels, which is a solid body, or you have a CD, we get a rotation. So if the period of the rotation is the same in a solid body, then in order to go around when you're on the outside in the same period that you go around in the inside where your orbit is much smaller, the velocity has to be proportional to the distance from the center. That's what we call solid body rotation. And we observe that in the centers, very centers of galaxies. But for most galaxies, we observe a rotation curve, as we call this, that rises very rapidly in the center. We have a solid body part that's very steep, and then it falls off a little bit and it wiggles around, but basically the velocity remains constant. And what that tells you, as opposed to in the solar system where the velocity falls off, that tells you that all the mass is in the center. When you get a flat rotation curve where the velocity is relatively constant as you go further and further out, that tells you that there's still a lot of matter out there exerting a gravitational force. The gravitational force doesn't fall off. It stays strong. And you can't account for that because the galaxy that you can see stops. And so we come with the idea that we have to have dark matter halos. And the history of this is that one of the first people who measured the rotation curve of M31 was Vera Rubin, who did this in 1970. Maybe you've heard of her. There's just been a stamp issued with her picture on it. And there's an observatory being built in her honor with her name on it. She got her master's degree from Cornell in 1951. She measured the rotation curve of the galaxy, Andromeda galaxy, and found out that the rotation curve was still flat as you moved out to the edge. It turns out that a few years later, my PhD advisor, Morton Roberts, and his colleague Bob Whitehurst measured even further out, further from the center, and also found that Andromeda was still, the velocity was still not falling off, even though you reached the edge of the galaxy. And then later on, they worked together with other people and found that this happened in all sorts of spiral galaxies. It was a common phenomenon. And so here's the picture again. If we look at Andromeda, here it is. As you go out, this is the part that Rubin and Ford measured, and this is the part that Whitehurst and Roberts mentioned, which was observed in gas. This is the starlight. The stars seem to end, but the mass does not. And that tells us that spiral galaxies must have dark halos that contribute a large part of the dark matter. Okay, then another thing that we can do is, I mentioned gravitational lensing. So let me explain what gravitational lensing is. Gravitational lensing is a phenomenon that was predicted by Einstein's theory of relativity in 1916. The theory of relativity predicts that space-time is warped around massive objects. And in particular, light travels along straight lines in space-time, but space-time is curved. And so Eddington in 1919 went out to see if he could observe this. So what he did was, at the time of a solar eclipse, when the sun's light was blocked out, he looked at a star whose position he knew should be blocked by the sun and the moon, which is lined up. But instead, he saw that star. And the reason that he saw the star was that here's the path, the actual path of the starlight. It follows straight lines in space-time, but space-time is curved or warped around the sun. And so the star's light actually traveled the yellow path. But if you generally assume that light travels in a straight line, it would appear that the star was over here. And the offset of this was a tiny fraction, just about what you could measure with a simple observation from the ground. And so he pretty quickly confirmed Einstein's very revolutionary idea that space-time was warped around massive objects. So the prediction was in 16, and he proved it in 1919. Well, nowadays, we can look for the same kind of phenomenon in much more distant objects. And so the way gravitational lensing works is it's gravity that's bending the light. It's not the construction of the lens as we're used to thinking of. It's not the diffraction of light as it moves through a piece of glass. Rather, it's the bending of light in space-time around a massive object. So gravitational lenses can cause the appearance of multiple images of a single background lens mass, and the structure of the images tells us what the mass and structure of the foreground lens is. So imagine we have an object in the background not perfectly lined up with the lens. Here we trace the paths of the light from the top and the bottom of the object as they get bent, as they pass by a foreground object which has mass. And so you end up thinking that the object is here and here when it's actually here. So let's take a look at some other examples of this. Let me first point out that there are a couple of differences between the way a glass or silicon lens bends light and the way gravity bends light. In an optical lens, the maximum bending occurs furthest from the central axis. In a gravitational lens, the maximum bending occurs closest to the central axis. A gravitational lens doesn't have a single focal point. But if the source, the lens, and the observer are perfectly lined up, you can get an image that is a ring. But if the lens is not perfectly lined up with the lensed object, you get some kind of a distorted image, which you can understand and model to figure out what the lens actually is. So let's remember that in this little picture up here, this is the lens and it's closer to you. And these are the images of the source, which is further away. Okay, so here's a nice little picture of, sometimes we do this with radio telescopes. We have a foreground back galaxy and a background galaxy whose light is bent. They're pretty lined up here. So we end up with a lensed image of the background galaxy. And this image has been created by the bending of the light from this object by the foreground galaxy. So the first ones of these were discovered in the late 1970s. And since then, we've found lots and lots of them, and we keep finding them. So here's an example of one. This is called the Einstein Ring Sloan Digital Sky Survey, blah, 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 blah. And it's nicely decomposed. Here's the image as you see it when you look with the Hubble Space Telescope. We can model that image as a background galaxy that is almost perfectly directly behind a foreground galaxy. And using our models of how the lensing works, we reconstruct what you actually see here, including these little lumps and bits. Remember, galaxies have structure in them. The shape of the image then reveals the geometry of the lens. And if you know the geometry, then you get the mass of the lens, the mass of the foreground object. So again, if we can observe gravitational lensing, we are able to measure the mass of the lens. And guess what? We always find out that there must be more mass to make the image. There must be more mass than we can account for in luminous matter. Okay, so sort of quickly to finish this up, depending on the shape of the lens and the geometry, you can end up with, for example, a spherical mass distribution. So here's the distant galaxy, here's the foreground object. We have an aligned spherical mass distribution. We get one of these, what are called Einstein rings. The blue is the background, the image of the background object, and the red is the lens. Sometimes maybe we have an elongated mass distribution. The lens isn't perfectly spherical. It, in this case, is more like a football, and we end up with a bunch of multiple small images. So a lot of interpreting the images requires us to model the geometry based on what we know about galaxies and how it works. So this is what we call an elongated lens, but they're lined up, and we end up not with an Einstein ring, but an Einstein cross. Okay, now, just the same way that galaxies can lens other galaxies, clusters of galaxies, which are much more complicated, like the Coma cluster, can also act as lenses to produce images of background objects. And it turns out we see that a lot. We know there's dark matter in clusters, so it's not surprising that they form images. So this blue that you see here, these streaks, all of those arcs are images of an object that is much, much further away than all these red galaxies that you see. But we are able to verify the mass of this cluster, we're able to measure the mass of the cluster in two ways. One is by interpreting the images of the background galaxy, and the other one is by measuring the masses of the galaxies and using that virial theorem to calculate the mass of the cluster. And whenever we do this, we always find out that the cluster must contain more mass than we can account for in stuff we can see. And that's dark matter. Again, here's just a little analogy of that. We have a dark matter in the cluster of galaxies, and the blue galaxy is here, and the light is bent to create the image that we see. So the bottom line is there is a lot of observational evidence for dark matter. There's another piece, which is understanding the cosmic microwave background and the structure in that. It's more complicated than I'm going to get into today. We'll talk about that another time. That would be a good topic to talk about sometime when you really want to blow your mind. But there is good evidence for dark matter in that galaxies and clusters of galaxies orbit too fast, stars and galaxies orbit too fast, and gravitational lenses prove that there are large masses. So then the question is, okay, if more than 80% of the matter in the universe is dark, and it's more like 85%, then what is it? And so that's what we're just going to talk about at the end. And there are two possibilities. There's baryonic dark matter candidates. Remember, baryonic matter are atoms and molecules and electrons and protons and stuff like that, stars, planets, neutron stars, which are like pulsars, black holes, which are related to the dead stars, black dwarf stars, which are stars like the sun, which were formed much earlier and have died, brown dwarf stars, which are objects that didn't quite make it. They're bigger than Jupiter's, but they didn't quite make it to be a star because they're not massive enough, planets, and rocks. Those are possible dark matter candidates. The other option are what we would call non-baryonic dark matter candidates, things that can't contribute too much electromagnetic radiation or don't contribute any electromagnetic radiation, but there could be a lot of them. So let's just talk a little bit about these two possibilities. Okay. The baryonic dark matter candidates, I call them baryonic, you could call it normal stuff. We understand more or less these objects. We know how they form. We know how they evolve. We think we know how many of them exist. Even if we can't see them all, we can take an extension of what we do know, because we may not be able to see them all because some of them are not don't give off electromagnetic radiation, but as we've talked a little bit about, we can look at the material around black holes. But when we take a complete census of all the objects that we can see, there's never anywhere near enough of these objects to contribute the dark matter we need to explain the motions of stars and galaxies and gravitational lensing. So, can't be baryonic dark matter. It's got to be something else. So on the other hand, we have these other possibilities. The neutrino, what we call weakly interacting massive particles, or WIMPs, cosmic strings, and modified gravity. Here's where I get to tell you very little, so we only have like one more slide because I don't know anything. Okay, so let's go through these. First of all, neutrinos. We actually know that neutrinos exist. We can study them. We observe them from the sun. We observe them from supernovae. And so here's the whole host of elementary particles that we know about that you might not be very familiar with. I hope many of you have heard of atoms and you've heard of protons and neutrons, but maybe you haven't heard of quarks. There are 6 quarks: up, charm, top, bottom, strange, and down. And they are subatomic particles, and they get together to make up protons and neutrons. And so we know about them. There are other particles which are called leptons, from the Greek word for light, some of which we know and love. And the one that we're interested in here are the neutrinos. Neutrinos come in different flavors, electron, muon, and tau, and there may be other flavors too, but we're not sure. And they're interesting because they are almost massless. They give off no light, and they interact with normal matter very rarely. And I like to quote that there are 65 billion neutrinos passing through your fingernail every second. There are lots of neutrinos, but unfortunately, recent measurements of the masses of neutrinos, it's really hard to measure them, their mass, because they don't interact with us. They pass through your fingernail and you don't know it. So it's really hard to measure the mass. It does not appear, they do contribute to the dark matter, but not enough to explain our problem. Okay, so let's talk about the others. These are non-baryonic matter, but in this case, I'm going to call this exotic dark matter because I really don't know what it is. WIMPs are weakly interacting massive particles. They're not massive like the sun or like a truck, but they're massive relative to the neutrino, for example. And there are a whole bunch of theories on the subatomic scale of what exists under very extreme subatomic scales in the very early universe about additional particles that are required to explain some of the phenomena that are understood. And these particles have mass, they do not interact with normal matter, and they give off light. And that would be great. That's what we're looking for. But the question is, do they actually exist? So the answer to that is we don't know. Then there's another idea that posits the existence of extremely long but very thin. And what I mean by thin, like the size of a proton, but really, really long. And people call them defects in space-time. I don't understand what that means. I just think of them as there's some kind of structure in the energy distribution of the universe that we do not understand. Remember, energy is equivalent to mass by E equals mc squared. So if you have these long, weird, stringy things that are very, 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 very dense, don't give off electromagnetic radiation, but can emit a lot of energy, then maybe that's what makes up the dark matter. But again, great thinking, but whether it has anything to do with reality is not known. And then there's the other possibility, which is that maybe we don't understand how gravity works. Maybe our theory of gravity is good for us here on Earth, but when you get to test gravity on very large scales in the universe, it doesn't behave the way we think it does. We need to modify. The same way that Einstein had to modify Newton's theory, maybe somebody else needs to modify Einstein's theory. Again, how, why, we have no idea. So the answer to this is neutrinos exist, but they don't have enough mass. There's little to no evidence of the existence of WIMPs. There's little to no evidence of the existence of cosmic string, and there's little to no evidence of the existence of some kind of modified gravity. So we end up in this conundrum of confusion, which I will leave you with to stay awake at night worrying about, that various independent pieces of evidence lead us to conclude that 85% of the matter in the universe is dark. We know what the dark matter isn't, so we're not totally lost. We know what it isn't, but we don't know what it is. And then, of course, as I mentioned, matter only contributes 30% to the energy density of the universe, but most of the energy in the universe is dark. So that's where we are. And I'll just finish here by pointing out that we've got 2 more sessions lined up for April and May, one at 7 p.m. and one at 4 p.m. And I'll finish there asking for questions. And I also will take topics if anybody has ideas you want me to talk about, if you send me an email, I'll think about it. Questions? Hank has a question.
Thank you very much, Martha. This has been quite fascinating. I really was taken with the image that was provided of the rotation around the center of multiple galaxies, and how someone figured out that that was what was happening. In time, how long does it take for that rotation to occur? I mean, are we talking that somebody was able to measure it over a year or a long time?
That's a great question, Hank. And the fact is, you make one measurement and you make one and you find out that the object is moving towards us or away from us, and you know how far away it is. So then you only need one measurement at one time, but you could calculate what the orbit is, making some very simple assumptions that the orbits are all circular around it. And when we measure the mass, so we measure the velocities of maybe 50 objects one time, but we can then make a model of how much mass there must be. Because yes, you're absolutely right. So just to give an example, back in the Milky Way, the sun is moving at 220 kilometers a second around the center of the Milky Way galaxy, and it takes us about 220 million years to make one revolution. For these galaxies and clusters, it's likewise, it's hundreds of millions to billions of years to go around once. So yeah, we can't wait. And that's why you can all say to me, well, how do you really know this? You have to make models. Well, let's go back and think about the solar system. Kepler figured out Kepler's third law. He didn't know very much, but he made the assumption that things work. So the model must be simple. So let's make simple assumptions and draw conclusions from that. And so maybe our simple assumptions don't work at all, but the fact is that there is this balance. And if you undo the balance, then things collapse or they explode.
Thank you.
And so back to how did the people figure out how to do with it? They were just extrapolating from what we know about the solar system. And we go back to the discovery of Neptune. It was because John Couch Adams was looking for the fact that when they watched Uranus move over periods of years, it was 50 years that they traced it before they could figure out that it wasn't quite where it should be. Again, they were making these very careful observations. They assumed it was a simple system and said, well, what could make it deviate? Well, what could make it deviate is if there was another planet that we didn't know about. David and Nina.
This is probably a really strange question, but back to the very beginning of your presentation, when you showed the picture of the eclipse of the sun viewed from the moon. If you were on the moon, would you have to use eclipse glasses to look at that? And could you learn the kinds of things that you can learn from the Earth about from the corona of the covered sun?
Yeah, you could learn about the atmosphere of the Earth. You would want to, whenever you could see the sun, you would take a look. You would need the eclipse glasses. And actually, I'm going to have to step out for just a second because the guys who are supposed to come at 5:30 are probably here right now. So let me just tell them that they have to wait. And then I'll come back.
Turn me off, please.
In the meantime, I can use this time to let you all know that we have a date for our volunteer appreciation / community celebration event. Sorry, the sun's kind of washing me out a bit, but we will be celebrating our volunteers on Sunday, May 18th from, let's see, I believe the time is 4 to 6 p.m. So please mark your calendars for that, and we will promote it as we go. And now back to Martha.
Okay, sorry about that. I've got guys coming and they were supposed to come at 5:30. I told them I was busy until 5:30, but they're here. They can do what they have to do. It's fine. Anybody have any other questions? Alan?
But that was certainly a wonderful, fantastic summary of all the gravitational arguments for dark matter. As you know, I'm sure there are a number of other experiments going on at the moment to try to actually seek dark matter. And aside from microlensing, which probably kind of alluded to the effect of in one of your comments, they all seem to me to be kind of model dependent, where you kind of, I mean, you really have to kind of assume some relatively specific physics to decide that they're actually going to work. Is that a correct impression, or what do you think about that aspect?
Well, right now I had to keep this sort of limited and not go through everything. In the case of, say, this gravitational lensing, the way you interpret the image is you have to say to yourself, what could make this image? And so you have to imagine a geometry of where the foreground lens is, where the background lens is, how it's lined up, what the shape of the galaxy that's doing the lensing or the cluster is doing. But again, you say to yourself, well, the average galaxies look like this. And yeah, they have some structure in them. Well, we can make a model of this. And not all models will work. Very few models will actually produce the image that you want. But indeed, you depend on a model. So a lot of the micro lensing that you refer to is gravitational lensing, where you can actually figure out if there are lots of little red stars by just staring at stars. And if another red star goes in front of one, it will produce an event where the object becomes brighter for a few minutes. And that brightening is not color dependent, which is very unusual for variations of stars. And so it has a very characteristic signature. And people did those experiments in the 1990s, and they proved that there can't be that many little red stars. Problem solved, which is why I didn't mention it. Then and so there's that whole class of understanding how many objects there are and how the dark matter can be distributed from studying that kind of thing. The other another example is you can look at what would the effect of dark matter be within a galaxy on very tiny scales. You need a scale that's big enough that you can trace what the dark matter should be doing, but you don't want there to be a lot of mass because that will, in stars, because that will overwhelm the dark matter. But you need to be able to observe something. And so people look at dwarf galaxies. Again, this is something that one of my graduate students did 20 years ago, but it was just incredibly hard and too frustrating to produce a result. But again, it's all based on, here's what I observe, and here's what I think can explain what I observe. And that's modeling. Now, there's a whole other category of experiments, which I didn't talk about, which is trying to look for the elementary particle related, the wimpy things. Those are looking for the actual particles. And those involve high energy physics experiments. And some of them are very interesting and may produce results in the next decade or two. Most of the time, what they do is they come to the conclusion, well, it can't be that kind of a WIMP. And it can't be that kind of a WIMP because they rule them out. But someday someone might find something. And that's in the realm of the elementary particle physics, where what people do in a lot of those experiments in these colliders, like at CERN, the Large Hadron Collider, is they take particles and they accelerate them in magnetic fields and they smash them together. And for a fraction of a second, they create the conditions that were like that the whole universe were like way back 13.7 billion years ago. And they can use those to create particles that don't normally, we don't normally find around or don't normally interact with us.
Thank you.
Okay, I'm gonna go see my guys who are gonna work on my house. But anyway, again, if you have any suggestions for topics, shoot me an email and I'll, if the topic is too hard, I'll find an excuse not to do it. But if the topic isn't so hard, then I'll talk about it. Peter?
Thank you,
did you have?
Martha.
You're muted, Peter.
How's that? Better?
Yeah, yeah.
Just a quick question in terms of definition. Is there a relationship between dark matter and event horizons?
Well, a vague relationship in the sense that an event horizon is just the edge of a black hole within which light cannot escape. And black holes could be one kind of dark matter. And we can't see inside the event horizon of a black hole. But we can see a black hole because we see stuff moving around it, which tells us the mass of the black hole.
Okay. Okay, thank you.
Okay. All right. See you all in a month or before.
Thank you,
some of you.
Martha.
Okay. Bye-bye.